This presentation will be covering wireless power transfer. This project was conducted at the University of Hawaii at Manoa, and this is a EE496 project. The project team members were Mohammed Abraham, Elena Barbour, Richard Kahakui, Makiko Kurihara, Justin Lum, Darren Martin, and Keith Nakamatsu. The introduction. The project goal was to investigate, study, and fabricate a wireless power transfer system using inductive coupling for powering a small device, such as a LED, a small motor, a small fan, then determine information about how the distance and interference by objects affect the wireless power transfer performance. There are two main components for this system: the transceiver system for power transmission, which includes the transmitting coil. Then we have the receiving system for reception of power, which includes the receiving coil as well as the device that needs to be powered. Here you're looking at the simulations conducted. For these simulations, we used the finite element method magnets software. On the left-hand side, we can see a graph that is showing the representation relationship between the number of turns and the inductance. So the more turns we made, we can see more induction happen. And then on the other slide, with this red dot representing a 40 centimeter loop with about 6 amps flowing through it, and this slide up here on the top right, it represents the magnetic field strength in relation to distance away from the coil. And below that, we can see an exponential decay of length away from the main coil. And this 40 centimeter coil, we're using 16 gauge, and there was 20 turns used. Here you're looking at the experimental data, and for the criteria, the primary loop, the transmitting loop, again was 40 centimeter diameter with 20 turns, and the secondary loop, the receiving end, was a 30 centimeter diameter with 15 turns. If we look to the right of this slide, we can see a graph that is representing the voltage versus the distance. And we were able to see that we got the highest efficiency at 6 inches away from our primary loop. And we were able to gather 13.4 volts at a distance of 6 inches. And we were also able to gather data of 0.69 volts at a distance of 31 inches away. Here you're looking at the results and analysis. So for the dimensions of primary and secondary coils were based on the simulations produced by the FEMM software as mentioned earlier. So we see here a 40 centimeter loop with 483.8 microhenries. Then we have 1.54 ohms with 20 turns and using 16 gauge wire. And 30 centimeter loop with 200.8 microhenries, 0.91 ohms, and the same gauge wire, 16 gauge. And on the right, we can see the minimal loss factor for varying coupling and quality factors. And here is the conclusion. So for the conclusion, larger coil size, the 40 centimeter, provided best transmitting for the magnetic field. And increasing the coil turns increases the field transmission strength. Adding coils in series actually improves the range, decrease maximum strength. And furthering increased frequency and coil turns both increased resistance. And these are our acknowledgments. We would like to acknowledge Dr. David Garmeyer. He was our advisor, and we would like to thank him very much for all the help and time he's put into assisting us in this project. And we'd also like to thank Ashakir Rahman. He has been a great help to us, and he has given us um, much help and experience in this project that we needed. Thank you very much. This concludes this presentation. Aloha. Have a nice day.